So far, we've been talking mostly about elements and atoms in the early part of the course. But for the most part, chemists deal with compounds, not elements and atoms on an individual basis. And these compounds have to have names, right? And a formula. And to be specific about a compound, and universally across a wide number of disciplines, the naming and the formulation has to be consistent. So we've come up with a set of rules of how to name and create formulas for compounds. So the first set we're going to talk about today are the binary ionic compounds. There's a bunch of other types of compounds, but today is just the binary ionic compounds. So to understand how ionic compounds form from elements, we have to go back to the periodic table to understand again where the components are of that. So recall, we know that the periodic table is arranged in increasing atomic number and grouped by similarities and properties. So again, the elements are grouped by their similarity and properties, and these groups are the columns that go down the periodic table. And then the rows, remember, are the energy levels of the valence electrons, and we call those periods. So using this knowledge, we're going to be able to write ionic compounds using a set of rules. So again, going back to the periodic table, we're going to have a couple of things that we haven't really talked a lot about during the periodic table construction, and one of those are the representative and transition metal elements. The representative elements are going to be all the elements that fall in groups 1, 2, 13, and 18. So those are these groups here, 1 and 2, and then 13, 14, 15, 16, 17, and 18. The other groups, 3 through 12, are we're going to call the transition elements, right? So we already know that these are the transition elements, but now these are going to get another name, if it's already not confusing enough, another name called the representative elements. And these down here are called the inner transition elements. But we're only mostly concerned with this whole part of the periodic table for moving forward. Once we have an understanding of the groups and periods in the periodic table, we now can assign these things called oxidation numbers. And the oxidation numbers are going to tell us how to form the binary ionic bond, right? Oxidation numbers tell us the relative charge of the atom within that compound. And oxidation numbers are assigned based on their location, the element's location on the periodic table. So all group 1 alkali metals are going to have an oxidation number of +1. All alkaline earth metals are going to be +2, that's group 2. Group 13 are all +3. Notice I skipped over 3 through 12. I'm going to get to that in a minute. Group 14, carbon and silicon. That is going to be either plus or -4 depending on the situation. We'll a little bit more about that in a second. Group 15, nitrogen and phosphorus, -3. Group 16, oxygen, sulfur, selenium, -2. Group 17, which are all the halogens, are -1. And group 3 through 12, which we call the transition metals, are going to vary. And we'll talk about a little bit about this later on too. This is just a visual on where the oxidation numbers are, right? So we can look here and you have +1 is the alkali metals, +2 is all the alkaline earth metals. Remember, we're going to skip over the D block or the transition metals. They're going to vary. Some of them are going to have +1, some are going to have +2, right? Now we're all into the other metals. We have boron, aluminum, gallium, indium. They're going to be +3. Here's the column where the transition is from pluses to minus, plus or -4. We got carbon, silicon, germanium, tin, lead. Once we over that little halfway point here, we're going to have -3 for nitrogen, phosphorus, arsenic, antimony, and bismuth. -2 is characteristic of oxygen, sulfur, selenium. -1 is for all the halogens and hydrogen. I know it's hydrogen is listed here as +1, but it really should be listed here as -1 for the halogen group. So remember back to the atomic structure chapter in the periodic table chapter, we talked about atoms forming ions, right? And the couple of things to remember again is that the metals, which are most of the elements on the periodic table and left of the staircase, are going to lose electrons when forming compounds, becoming cations, positively charged ions. All the nonmetals, or the elements to the right of the staircase, and hydrogen are going to gain electrons when forming compounds and become anions. So they're going to become more negatively charged. That's what it stands for, A negative ion, and cation means, positive. So negatively charged ions are going to form with the nonmetals, and the metals are going to form the cations. An ionic compound now. An ionic compound will form between two ions. You need to have a cation and an anion, or you could have several cations and several anions. But the bottom line is you need to have at least one cation and one anion. Again, a cation is an atom that loses one or more electrons. Its positive overall net charge, and essentially all the cations are going to be metals. Anions, on the other hand, are going to be formed when an atom gains one or more electrons. Gaining electrons makes it more negative, so the overall net charge on an anion is going to be negative, and they're going to be essentially all the nonmetals on the periodic table, or to the right of the staircase. When two ions of opposite charge get together, they're going to form what we call an ionic compound. Remember, ion and then ionic, so ion compounds. So when the metal atom transfers its electrons, because remember it wants to lose electrons, to a nonmetal, which wants to gain electrons to complete the octet, a cation and anion form, and then the ionic bond is due to the electrostatic forces that are created. Okay, so let's see how an ionic bond forms. So remember, when our elements or atoms of elements are in their natural state, they're neutral. However, when you bring them together, there could be a chemical reaction between the two, and that results in the formation of a new bond. So recall that sodium is an alkali metal, and chlorine is a halogen. Both are very reactive on the scale of reactivity, because remember, the sodium has only one valence electron in the third Euler level, and it wants to look more like neon before it and have a full valence shell, which is the 8 electrons here. This one electron kind of makes it unstable, and therefore it wants to get rid of it as soon as it can. On the other hand, the chlorine atom has 7 valence electrons. It's looking for another valence electron to fill that 8 valence electron shell. And so therefore, when these two elements get together, the high electronegativity of the chlorine atom is going to want to acquire the electron from the sodium atom, and the sodium atom has such a low ionization energy that it's going to be almost instantaneous. So the electron will donate from the sodium atom into the chlorine atom, and therefore now when we do this, we have a full octet on the sodium ion and a full octet on the chloride ion. So we have a cation and an anion, and now these two will get together because opposites attract. Now, as mentioned, chemists and scientists need a system for naming compounds that's universal across the world. Otherwise, we'd be talking about different things to different scientists. So, for example, sodium chloride to me might be something different than sodium chloride to you if we don't have a universal naming system. So the naming system that we're going to use with ionic compounds is called the Stokes system, right? The Stokes system. So you'll hear me say a lot of times, ionic compounds stock system. So the stock system is used to determine the formulas for binary ionic compounds. Sometimes you also hear this called name to formula for ionic compounds. Now remember, binary ionic compounds only contain two different types of elements. So I'll give you some examples here: potassium chloride, sodium fluoride, and magnesium chloride. Now you would say that, why is magnesium chloride a binary compound? Because it only contains two, chlorine and magnesium, different atoms. Even though there's a little 2 here on the bottom, it contains 3 atoms total, but the magnesium and the chlorine are the only 2 elements involved. Also, once we form an ionic compound, the total charge over the whole compound is neutral. The ions themselves will be charged, but the net overall charge of all the cations and all the anions must be equal. And so here are our simple rules for writing formulas from names. Step 1 is to write the symbols for the elements involved. We're always going to write the metal ion first, or the cation first. Now we're going to assign our oxidation numbers to each based on their location in the periodic table and the rules and the things I gave you. So all alkali earth metals are going to be +2. All alkali metals are going to be +1. All halogens are going to be -1. Right? So here's where it gets a little tricky. You're going to drop the charges, the plus and minus, and crisscross the oxidation numbers to form the subscripts. Anytime you have a subscript of 1, you're going to omit it. And then when you're done, you're going to reduce the subscripts to the lowest whole number ratio. Let's see how this works on the other page. Okay, so let's see how this works using our rules, right? So we're going to now use the names and create the formula. So ionic formulas from base elements, examples. So my first element is calcium, and my second element is bromine. So calcium is going to form my cation, bromine is going to form my anion. So the first rule is we're going to write down the element Kimball symbol. We're going to do that here, calcium, and then we're going to write down bromine. It's the second symbol. Now we're going to assign the oxidation numbers for each element. So my calcium is in my alkali earth metal group. Those are all +2, so we put that right here. Bromine is a halogen, and therefore it's always -1, so we're going to put that here. Now the next part is we're going to combine the two, but let's go over here and show you how we do this. So we have 2 calcium, 2+, and we're not going to write the plus anymore. We're just going to put a 2 here, because we already know it's 2+, and then the bromine we're going to put the 1. Now we're doing the crisscross, so we're going to take these 2 numbers and move them down from the superscript bit down to the opposite side for the subscript, and then we get Ca1 Br2. Now as we said in the rules, we never write the 1, so this becomes Ca Br2. And there you have it. So there's how we write calcium bromide. Let's look at another one, potassium and nitrogen. Right, so we're going to do the same thing we did before. We're going to write our chemical symbol, which for potassium is K, and then we're going to write our chemical symbol for nitrogen, which is N. We're going to assign our oxidation numbers, +1 for calcium, because it's in the alkali metal group, and nitrogen is going to be -3 because it's in group 15. So again, we're going to do the thing over here. So we're going to have calcium, and we're going to put the 1, and then we're going to put N, we're going to put the 3, we're going to do the crisscross, so we get K3, I'll write that real quick, K3, N1. Again, we don't write the 1, so it becomes K3N. You can see now this is a pattern here. We can do the same thing with sodium chloride right? We're going to take the 1s and we're going to switch them. Since we don't write the 1s in the superscript, it just becomes sodium chloride. Now, we've always had one of these elements have a 1 charge, either -1 or +1. So here's my -1 here and a +1, and then these are two minus and pluses. Let's look at a system where they're non plus or minus 1 for the oxidation numbers. So aluminum and oxygen is a good example of this. So aluminum and oxygen. So let's look at that real quick. So we have aluminum. We know that's +3 because we've assigned it here. And then so we're just going to write a 3 here. And now we also have oxygen, 2-, so we're going to write a 2 here. Right? And then again, when you start doing this by yourself, you're going to be very good at not even have to write these. You're just going to know off the bat. So we're going to do the crisscross again. But that one goes here, that one goes here, and you're left with Al2O3. Okay? Now the thing is, one of the other rules, the last rule, is we can't leave anything in a non-whole number, right? So we can't have any fractions. So if we try to reduce this by dividing one side by 2, we get Al1O1.5. That doesn't work. We need to have a whole number. So this is the lowest whole number combo that we can do, a 2 and a 3. Okay, so here you're going to try and do the same thing that I just did on the previous pages. So you're going to look up your element on the periodic table, find out what group it's in, assign an oxidation number, and then do your crisscross and see if you come up with a compound. So right now you want to stop the video, write down the information here, work the problems, and then when you're ready, start the video. So stop the video now. Okay, you should have gotten these answers. Lithium bromide should just be 1 lithium and 1 bromine. There's no subscripts of 1 because we don't use subscripts of 1. Calcium iodide is very similar to calcium chloride. Remember that all the iodides, chlorides, fluorides, since they're all in the same group, the halogens, they should have all, and they all have the same valence number, and they all have the same oxidation number. When combined with a alkali earth metal, they're all going to have roughly the same formula as far as the ratio of alkali earth to halogen. Francium and fluorine, francium is +1, fluorine is -1, so the ratio there is 1 to 1, and that's how it's written. Aluminum chloride, remember aluminum is +3 and chlorine is -1, so we need 3 of the chlorines to balance the +3 on the aluminum side. And then on sodium oxide, we have a +1 for sodium. We have 2 of those, so that's +2. And oxygen is always -2. And therefore, we have a net charge of 0. So if you got those, that's pretty much it as far as the technique to do it. And it shouldn't be any worse than that. So if you got them, great. If you didn't, go back and review a little bit and do some more practice. So you may have noticed that when we name ionic compounds, we don't use the full name for the anions. For example, we don't use magnesium nitrogen or lithium oxygen. The anion is always named with some type of IDE after it, right? And we need to have a system of how to recognize that. So instead of trying to come up with a series of rules, we just want to memorize or look at a simple list of elements that then become the ides of them. So carbon, for example. Carbon, we drop the ON in carbon to make carbide. In nitrogen, we drop the OGEN to make nitride. Oxygen, we drop YGEN to make oxide, etc., etc. So when we're done, we have the element itself is named here, but the counterpart for the ion name is named here. So carbide, nitride, oxide, fluoride, etc., right? So when you see the word carbide or the word silicide or oxide, you're going to always assume that now we have an anion of oxygen, right? O2-. So the nitride would be the nitride would be N3 minus, the oxide would be O2 minus, right? That's what it means, right? Oxygen is a neutral atom, the oxide is the anion of that neutral atom. Okay, so here's some examples. So this is going from the name to the formula, right? So I'm giving you the name now instead of just the individual elements, right? So in this case, I'm giving you sodium fluoride. So we know that the cation is going to be the sodium, and then the fluoride is the anion. So this is my cat, and this is my anion. Cation, anion. Calcium, again, is going to be my cation because it's my metal atom. Magnesium, again, cation. Boron, again, cation. And then the rest of them, the bromide, the oxide, and the other oxide are all going to be my anions. So you can see here, so once I know this is my cation, here's my cation. Fluoride means F minus, and then I get my chemical formula here, right? Now let's look specifically at this one here. If you were to do it by the convention way that I just showed you with the crisscross, you would get Mg2O2. Now I can tell you that Mg2O2 is not the correct formula for magnesium oxide. Magnesium oxide is written MgO. Now, why is MgO the more correct version of Mg2O2? Because we just did the crisscross, and the crisscross, I've been telling you, gives you the subscripts. The actual rule that we have to follow, for the last rule, is that the formula has to have the elements in the lowest whole number ratio. So if I take MgO2O2, I can reduce that even further by dividing each element by 2 to get MgO. Right? I haven't changed the ratio. It's still 2 to 2 or 1 to 1, but now it's the correct ratio. So MgO is the actual correct way to write it because we've reduced it, the ratio of elements, to the lowest common ratio. Okay, so at this point in the lesson, you're going to try it on your own. So you're going to look at these 5 compounds, and they're all ionic, and you're going to make the correct structure with them using the techniques that you've learned in the last few minutes of the video. All right. When you get down to silicon nitride, you're going to treat silicon as it has a +4 oxidation number. Right? So remember, silicon is in that column that has +4, -4. So you're going to treat it as a +4. Treat it as the cation in that particular compound. So you can stop the video now, start it when you're ready to go, and that's the end of this. So good luck.